Look up on any clear day, and the immense physical footprint of global aviation is etched across the sky. To achieve its collective net zero carbon emissions target by 2050, the global air transport sector must secure an estimated 500 million tons of sustainable aviation fuel, or SAF, every single year. This chart maps the trajectory of required demand against projected supply. Entering 2025, global production sits at a mere 2 million tons. The shaded red area represents an exponential deficit scaling toward 2050. The current infrastructure is completely inadequate to close this gap. Concurrently, the global regulatory environment is rapidly tightening. Under Europe's Refuel EU mandate and other international frameworks, airlines are transitioning from voluntary corporate goals to strictly enforced compliance targets starting in 2025. If fuel suppliers and airlines cannot source that missing 500 million tons, they will face severe regulatory penalties that will systematically erase their historically thin operating margins. Currently, roughly 60. Congress amended the 45Z tax credit to entirely exclude imported used cooking oil, which forces domestic SAF refiners into fierce competition for limited local agricultural supplies. Relying on first-generation domestic crops to fill this void is mathematically inefficient. It takes an entire bushel of soybeans to yield less than a single gallon of sustainable aviation fuel. Attempting to extract 500 million tons of fuel from these legacy lipid feedstocks will drive up agricultural commodity prices and trigger severe global food shortages. The industry must pivot to non-food biomass. Advanced lignocellulosic biomass, specifically industrial hemp and bamboo, provides the exact agronomic properties required to bypass the lipid bottleneck without triggering land use conflicts. Industrial hemp operates on a highly aggressive 120-day growth cycle. It thrives on marginal land, requires minimal chemical inputs, and actively remediates degraded soil. Advanced hemp genetics offer a dual revenue conversion track. The seeds provide a high-yield lipid oil that can be injected directly into existing heifer refineries, while the vast majority of the plant's volume, the stalk, offers massive cellulose reserves. Through advanced pretreatment techniques like steam explosion, the recalcitrant lignin in the stalk is separated. This process isolates the fermentable sugars that serve as the primary chemical input for the alcohol-to-jet pathway. Where hemp provides high-density lipids, bamboo provides sheer volumetric scale. Bamboo accumulates biomass 10 times faster than traditional timber and sequesters immense amounts of biogenic carbon in its root system. Because bamboo does not contain extractable lipids, its conversion to fuel requires a completely biomass-agnostic approach. The solution is thermolysis. By superheating raw bamboo in an oxygen-starved environment, the molecular bonds break down. This produces a hydrogen-rich synthesis gas, alongside a solid biocarbon known as biochar. That synthesis gas is the foundational building block required for the Fischer-Tropsch synthetic fuel pathway. Mastering these specific chemical conversion pathways allows the aviation industry to map high-yield, net-negative carbon crops directly to its massive volumetric demands. Regardless of agronomic superiority, alternative fuels face rigid global safety parameters. Aviation turbine fuel is strictly regulated by the ASTM D7566 standard. Under current ASTM annexes, synthetic fuels derived from both the Fischer-Tropsch and alcohol-to-jet pathways are capped at a maximum 50% blend ratio with conventional fossil jet fuel. This cap is dictated by a specific chemical limitation. Synthetic fuels derived from hemp and bamboo are entirely paraffinic. They contain absolutely zero aromatics. Aromatics are specific hydrocarbon rings that interact with the elastomer seals inside aircraft fuel systems, causing them to swell. Older legacy engine architectures require between 8% and 25% aromatics to maintain the integrity of these seals and prevent catastrophic mid-flight fuel leaks. Maintaining these aromatics comes with a severe environmental trade-off. Their combustion directly causes the formation of soot particles, which generate high-altitude, climate-warming contrails. To address this, the aerospace industry is aggressively testing 100% synthetic flights. Modern engine architectures are built with advanced synthetic seals that do not require swelling from aromatics to operate safely. Bypassing the 50% blend wall to achieve 100% synthetic lignocellulosic flights will eradicate life cycle carbon dioxide emissions while simultaneously neutralizing the massive non-CO2 warming impacts of aviation. Inside airline treasuries, the macroeconomic pressure is forcing a complete reevaluation of risk. The traditional financial framework of hedging operational costs exclusively against fossil fuel indices is obsolete. The aggressive introduction of carbon pricing, specifically through the EU emissions trading system, converts exhaust emissions directly into hard, unhedgeable balance sheet liabilities. Holding standard Brent crude futures offers an airline zero financial protection when regulatory carbon allowances suddenly spike to €100 per ton. The modern treasury strategy treats the physical acquisition of SAF, through long-term offtake agreements and direct equity stakes in biorefineries, as a complex, dual-purpose financial derivative. This chart illustrates the dual hedge. Securing high volumes of ultra-low carbon intensity SAF protects the airline against fossil fuel price shocks. Simultaneously, the physical procurement of that SAF proportionately erases the airline's required purchases of expensive ETS carbon credits. Airlines that fail to integrate SAF as a core financial hedging instrument will see their operating margins destroyed by the compounding costs of carbon taxes and regulatory blending fines. The massive capital required to build advanced agricultural refineries is driving a geopolitical shift. The locus of energy production is migrating from traditional petrostates toward equatorial bioeconomy hubs. Landmark projects are successfully capturing this refinement locally, from Ghana's $1.3 billion Amaba bamboo biorefinery to comprehensive legislative frameworks for hemp industrialization in Kenya. This creates a logistical paradox. Physically shipping finished hemp or bamboo fuel across oceans destroys the fuel's highly prized net negative carbon intensity score. The structural solution is the book and claim digital accounting framework, which decouples the physical SAF molecule from its environmental attributes. This diagram illustrates the decentralized bioeconomy. Local bamboo and hemp are processed into fuel and injected directly into equatorial aviation grids, eliminating oceanic shipping emissions. Meanwhile, Western airlines purchase the corresponding digital certificate, claiming the environmental attributes to legally satisfy their compliance mandates. The physical fuel decarbonizes the region where it was grown and refined, while the capital flows globally. This digitally enabled, decentralized bioeconomy represents the only scalable, mathematically sound pathway for the global aviation industry to survive the multi-decade energy transition.